Okay, so let's look at key exchange and the mechanisms that make that work. So this is the Diffie-Hellman method here that we'll outline, and that'll be one of the first topics that we outline. From there, we'll look at some of the weaknesses that we have within the Diffie-Hellman method, and then how we can move on to use the elliptic curve Diffie-Hellman method, which is a much more efficient way of implementing the approach. Then another way that we can pass a shared key is using public key or asymmetric encryption. And then finally, we'll look at how we can manage these keys that we might use in a key exchange. Okay, so this is the basic model that we have for Bob and Alice to communicate. So normally we have what's called an encryption tunnel between Bob and Alice, and that tunnel is encrypted with a shared symmetric key, such as with AES or Cha-Cha-20. So the problem that we have is, how do we get the key from Bob to Alice? One way we'll find is with public key encryption, but the more typical way is that we have a key exchange method where Bob and Alice can openly communicate and then both derive the same shared key in the end. So where does the tunnel start and end? Well, in TLS, we typically look at the network stack. So if the application is here and here, then there is a gap between the application and the network stack. So someone could put a proxy in here to be able to listen to the communications, because this part here is non-encrypted. The bit in here will be encrypted, and then the bit between the application and the network connection or the network API will not be encrypted. So the tunnel is not implemented. For end-to-end encryption, then the applications or the services will be able to communicate and negotiate the key. This is a major problem for any organization who wishes to check the data in the tunnel. So often what can happen is there's a break in the tunnel, and with that break, then it is possible to implement intrusion detection systems, virus scanners, and so on. But for end-to-end encryption, it's not possible to break the tunnel because the keys are generated on either side. This is known as end-to-end encryption, and these are some applications which use end-to-end encryption: Signal, WhatsApp, Wire, Viber, Riot, and Telegram. You can see they've each got their own basic features for their overall security setup. And if you're interested, this paper here will outline some of those features. But end-to-end encryption is between the application and on the applications on either side. So let's have a look at the basics of the Diffie-Hellman method and how it works. So the problem that we've got is how we get the key from Bob to Alice without Eve actually discovering it. And this was solved by Whitfield Diffie and Marty Hellman, and they created the Diffie-Hellman method and allowed Bob and Alice to openly communicate, and for Eve to even listen to, Eve listens to the communications and cannot derive within a reasonable time or within a reasonable cost the key that Bob and Alice has generated. There are two basic principles within inside key exchange that we'll come back on to a little bit later in the lecture, and also later when we look at TLS. But we have forward secrecy. With this, it is possible to compromise the keys if we have a master key between Bob and Alice, and then there are derived keys from here. It is possible that if the master key is hacked in some way, then it is possible that the other keys will also be compromised. And then we have ephemeral, and with this we use standard parameters, so that it might be possible for an intruder to build up large tables of possible parameters and then compromise the system. So how does it work? Well, it uses discrete logs, and if you remember, discrete logs is the a to the power of b, g to the power of a to the power of b is equal to g to the power of ab. And in discrete logs, we bring in the mod of a prime number. And with this, we typically pick a value of g and p. G is called the generator value, and p is called the prime number that we're going to use. This will typically be greater than 1024 bits. This might typically be 2, 3, or 5. So basically, Bob creates a secret, a value between the 0 and the prime number -1, and Alice will do the same. Bob calculates b, which is g to the power of little b mod p, and Alice generates g to the power of a g to the power of a mod p. They then exchange the values. This is the value of a. So Bob takes his secret, takes Alice's value and raises it to the power of b, and then the other side takes Bob's value and then raises it to the power of a. Then the value, because of this rule here, the value they'll generate is g to the power of ab mod p. So let's give that a little try here. Okay, so we'll generate some Python. So let's take a value of g equals 3 and p equals 997. It's a prime number. And a is 23, and we'll say b is 62. Okay, now we'll generate Alice's value, which is g to the power of a mod p. And Bob's value will be g to the power of b mod p. So we'll just print out the value that Alice sends and the value that Bob sends. That's great. Now, Alice's key will be b, which she gets from Bob, to the power of a mod p. And Bob's value will be a to the power of b mod p. So fingers crossed, hopefully they will end up being the same value. Try this one, and it is. Okay, so Bob and Alice have managed to do it, and through the magic of the mod p operation, then all our normal maths will work. Okay, so there's an example there. Bob generates 7 and Alice 9. There's the computation to give 40, 30, and the values go over here. And we can see here that we end up with the same value there. So if I show you a simple example here, generate a g and an n value, generate random values here, and then hopefully we end up with the same shared value in the end. Okay, but we typically don't just take that value and make it into a key. We put it through the HKDF, which takes a salt value and the secret together and then generates the key. So obviously we will use the Diffie-Hellman method to generate the secret, and then Bob and Alice will have some way to have the salt value generated that goes into this function here, and on either side they should create the same encryption key for their tunnel. So what about the value of the generator, the g value? Well, it relates to the prime number that we pick, and we've got to make sure that the g value, the generator, actually works with the prime number. For this, we need to make sure that all of the outputs that are possible between 0 and p-1 all occur, and we don't get a repetition. So if we take 2 to the power of x mod 11, so we'll take 11 in this case, and we work out 2 to the power of 2 mod 11 is 4, and then we get 8, and so on. So we can see here that all the values of our output are between 0 and p minus 1. So this one works. But look what happens here when we take 3. It's now repeating again. This one's repeating, this one, and so on. So this one's not possible. Neither is this one or this one. But this one is fine. And also this one looks okay. So we pick a value of g for the prime number, or we start with a g and we just make sure that the prime number will fit. So we tried 11, so there we go, 2, 6, 7, 8 was what we found out. So let's try 73, 5, 11, 13 and so on. Let's try 97. And those are the possible generator values in here. So it's not a difficult piece of code that we have. Just this little bit of code here allows us to find the g value. And normally there's a value of 2, 3 or 5 that we can use. So 2, 3 is used here. We could use 2 here. And we could use 2 here. 5. So typically it's a 2 or a 5 that we would use, or a 3 as our generator value. Okay, so in real life we have very large prime numbers. So we define these in groups. A 768-bit is a group 1 prime. That's not very secure. Group 2 is a 1024-bit prime. Again, it's not secure. And this is typically where we start at group 5. So in this case, what we can see is we're generating our sets of parameters that we're going to use for our Diffie-Hellman key exchange method. So there's our prime, 768 bits, and there is our generator value, or our g value. So let's see if we can generate our keys, our parameters, and see how long it takes for this to happen. So let me find that. So first we'll compute 738. Okay, doesn't take too long. So let me see what that looks like, and there we go. So this is a 738-bit prime, and we're using a g value of 2. So now let's go for 1024, which is our group 3. Takes a little bit longer to do this. Okay, but it gets there eventually. So now we can see we have a 1024-bit prime. So it's continually searching. So it takes a random number and then random odd number, check if it's a prime, add 2 if it's not, and then keep going up until it actually will find a prime number. That's why it's taking so long to do that. And then it needs to check that the g value works with it. But let's try with 2048, which is much larger. Well, it was actually quite quick there. We could be lucky that it generates it quickly, but you can see this time it's actually taken a bit longer. So we could be lucky when we're generating and get one quite quickly. So we've eventually got our 2048-bit prime number, which is fine, and we're using a value of g. Okay, so those are our basic parameters that we use, and we can also define this in a base64 format with this here. That defines the parameters that we're showing here. Okay, so what are some of the weaknesses? Well, this paper here showed that that there were many sites that were using a standard default for the values of g and p, which meant that someone could actually build a table of values to be able to generate the encryption keys and then eventually crack the session. And this was one of the defaults here, that the administrators hadn't changed they hadn't generated the parameters, and they were using this default site here. 7% of the top 1 million sites found that it was hard-coded into the service, and 3% were still using the default parameters. The other weakness that we have is Eve in the middle, where it's not possible for Bob to actually know that he's really communicating with Alice. Eve could be in the middle, and Eve will negotiate two keys between Bob and Alice, key 1 and key 2. This will encrypt, then decrypt, and then re-encrypt with key 2. In this case, we have Eve's key here, and we end up with g to the power of EB here, and g to the power of EA there, which are two different keys. And on the other side, there'll be two different encryption keys. So how do we make sure that we authenticate Alice? For this, we have the public key, and the public key is then used to be able to authenticate the connection. So the public key is passed from the server to the client and checked with its signature. We then compute what's called the pre-master key, just like we saw before with the Diffie-Hellman method. That becomes the master secret. Then we can feed that into a random function to create the master secret. And then for each of the keys that we're going to use, we create a nonce or a random seed value. This then creates the key that we're going to use for the session. And for this, we need to obviously pass the nonce value between Bob and Alice for it to work. Okay, so now let's look at the elliptic curve Diffie-Hellman method. So for this, rather than using g to the power of x, an exponential, we use a multiplicative. We take a point on the curve and we multiply it by a scalar value. This value is our private key. Basically, we take the point on the curve, we generate a random private key value, typically 256 bits, and then we multiply that with the base point to get our public key point. Basically, it's almost like adding the point priv or the secret key times. So this shows our private key. In this case, it's a 256-bit private key, and then this gives us our public key here, which is an XY point. Then this is our generator point here, which again is an XY point. So here are the parameters that we have. There's the private key, the public key, and this is the curve that we're using. And these are the parameters, because remember, in this case, we have this type of format, 0 and 7 there. There's the generator value, there's the prime number that we're using, and this is the total number of points that we have on the curve. The 0,4 here identifies that this is an uncompressed point, which means that it contains both the x value and the y value. If we saw a 2 or a 3, it's a compressed value where we only get the x value. So the key this is 4. Over here. So the 0,4 identifies uncompressed. And if we had a 0,2 or a 0,3, then we only store the x value here. And it identifies whether it's an odd or an even y value. So that compresses the point down. So this is uncompressed and this is compressed here. So the way elliptic curve Diffie-Hellman works is with this multiplicative operation. This is the private key of Bob and Alice that's generated. Then we'll multiply that by the generator point and we get a public key value for each session. That's passed over, and again we just multiply this time. So we end up with dA dB times g, and because it doesn't matter which way we multiply, then we end up with the same shared key on the other side too. Okay, so we'll just look at an example of that one. So let's take this curve here. These are the basic parameters as we saw. There's the base point here, and there's the prime number that we're using for this curve. So let's generate an A value. That'll be between 0 and the prime number -1. And this is a random number here. We'll compute Alice's public value, Bob's public value, derive the secret, and hopefully they'll be the same there. Okay, so this is the point on the curve. Typically, we'll just take the X value and use that for the key. So Bob and Alice will take the X point value and then just use that from there. So we can take a smaller key value. So there we go, we'll take this smaller curve and hopefully we'll end up, so that's the point, and derive the secret, fingers crossed, that's it derived. Okay, and it's very, very fast indeed. Even if we went for a larger curve, then it doesn't actually take that long to generate the keys. Okay, and we use this in the Tor network. So in this case, ECDH is used to be able to negotiate a key between each of the Tor nodes. So we've generated a purple key, a green key, and a red key using elliptic curve Diffie-Hellman. So when Bob has 3 keys, we'll encrypt with the red, then the green, and then the purple. Then we'll take the purple key off when we get to the first node. When we get to the next node, we'll take the green key off. Then when we get to the last node, we'll take the red key off. And then we'll have the data in the end. So this is an onion routing approach where we secure the nodes so that none of the nodes can actually see the data. This is known as the exit node, and this is known as the entry node here. When it comes out of here, it's unencrypted. It can still be tunneled, but the Tor scope has finished at this point here. If you're interested, we actually use curve 25519 to be able to generate these keys. So curve 25519, we typically define that as X25519 for the key exchange. And then for these two typical curves, we define that as ECDH. For a larger curve, such as 521, then we would define that as X448. This is for high security, this is for acceptable security. So we can also pass the key through public key encryption methods. So this has been used up to TLS 1.2, but has now been dropped in TLS 1.3 because of the long-term hack of the master key. So for this, Alice, who might be Google, sends over the public key in a trusted way. Then Bob will encrypt the key that he wants with her public key, sends it over, and she uses her private key to be able to reveal the key that Bob wants her to use, and then they'll both have the same shared key. As I said, then the problem here is that if Alice's private key gets hacked, then all of the keys that Bob and Alice have used in the past could be revealed. So finally, let's look at key distribution centers, and this allows us to be able to manage our key infrastructure in a more trustworthy and auditable way. So we might say that Bob is allowed access to this device, but Alice isn't. And how do we make sure that we keep all the keys that we've used so that we can actually audit things and we can keep it all secure? For that, we create a trust infrastructure for our keys and where we can define the rights of access. So the way it can work is that we have a trusted key distribution center, in this case called Trent. It will store Bob's key and Alice's key securely, and now Alice wants to communicate with Bob. Alice doesn't go to Bob directly, Alice goes to Trent and Alice asks if it's okay to talk to Bob. So Trent will now create a new key for the connection, and then we'll seal an envelope with Alice's identity and the new key, and then encrypt it with Bob's key. Next, he'll wrap it up with the new key and the sealed envelope for Bob, and then encrypt with Alice's key. That's then sent over. Now Alice can open up this and will reveal the key that's going to be used, this one here, and then send over the sealed envelope to Bob. Bob will use his own key to open it up, and he'll check that it's got Alice and there's a new key in there. So Alice and Bob know that only Trent can have the key for their own keys, so that everything is trustworthy here. Okay, here's a very simple way that can actually work. In this case, the KDC, or the Key Distribution Center, becomes the kind of central place for communicating with Bob and Alice. An improved way, as we saw, is for Alice to request, there's the keys being stored, Alice to request the Key Distribution Center. We get the two things back, that the encrypted version of Bob's session key. So here's the session keys. That's encrypted with Alice's key. This is encrypted with Bob's key. Comes back, and then in the end they'll end up with the same shared key. A more advanced version of this is what's called Kerberos. I won't go into the detail here, but again we store Bob and Alice's key, long-term key, in the Key Distribution Center, and then the KDC will actually create the session key. Then we have this interlinkage that looks at the timestamps and so on to make sure that it's all synchronized, but in the end we end up with the same shared key. It's a fairly complex implementation, but this is an example here with the IDs, and here are all the parameters passed, and then in the end hopefully Bob and Alice will have the same shared key. Okay, so that's been an overview of key exchange. We went through the Diffie-Hellman method, some of the weaknesses of it, then how we extended that into the elliptic curve, because we went from g to the x to x times g, and that's a much easier computation. Then we looked at why we can pass with public key encryption, and then finally we went on to how we can create our own key distribution center and to create our own trusted infrastructure. Okay, thanks.